Well, so ideally, these are, or particularly the solvings. Um, I did note up there that I moved some of the due dates and the test. We started this section a couple days back um, because we had the first test a couple days back. So this is all just kind of moving accordingly. I thought about trying to do these sections a little bit faster, but I don't want to rush us through them. They're fairly important sections, particularly the solving. So ideally, you've got that 7.3 done already, but the 7.4 and 7.5 will move to Thursday and have the test on Friday. That seemed to work out okay last time. If any of those date changes, and all those dates should be changed on MyOpenMath already. So if any of those date changes cause any issues, let me know. I also moved the dates, or moved the other exams and some of the other sections that we have. So all of the dates on MyOpenMath should now be current through the rest of the term, assuming nothing else weird happens. So, but if any of the new dates cause any scheduling issues, let me know. Now, these solvings do take some practice, so I did want to make sure we have a chance to talk about them a little bit more. So for this one, anything weird happen on this first one? If so, what happened? Nothing weird happened? You got some nice handy solutions? You guys are not going to have one of those quiet days, are you? The sine inverse of the 5/3? Yeah, what happens when you take the sine inverse of 5/3? We haven't seen any examples when this happens. But yeah, we know sine doesn't output anything above or below +1 or -1. So asking what x values make this sine function output 5/3, sine never outputs 5/3. So as soon as we get something like that, really before even taking the inverse, we can recognize, but you usually will just by habit try to find the inverse, and it'll say no, it'll say error. So at that point, it's just no solutions and you're done. It's always scary when that happens on tests because you're like, oh no. And we are not learning about imaginary trig. There is no imaginary trig functions, or not like that anyway. So yeah, it just goes to no solutions. So I did want you to make sure you guys see that at some point, because it's actually not uncommon to have it occur. When you've got oscillations trying to line up, sometimes the oscillations don't line up, and this is what happens when they never do. In some ways, it's nice because the problem's done; it's over. In some ways, it's bad, particularly on exams, because it does make you really nervous, like, oh crud. But yeah, no solutions. It happens. Similarly, sometimes on sections on inverses, you'll see problems like, what is the cosine inverse of, 5/3? And it's just, there's just no answer. The cosine inverse of 5/3 does not exist. So sometimes you'll see that happen, and it's good to kind of be prepared for that. As opposed to, however, if you were given the secant inverse of 2, secant can be bigger than 1 or -1. Frankly, it has to be bigger than 1 or -1. So that would just be the cosine inverse of 1/2, which would be, what, pi/3? So we do want to be ready for that. But because of that, it might be nice for us to practice another one of these where that doesn't happen. Oh, I want to go minus something fun. How about minus 5 pi over 3, and then, oh, I want another, no, plus. Plus is nice. Plus 2. So in a minute, I'll give you a chance to solve that. It will be something that actually has some solutions to it, so we can practice that. But first, let's talk about this simplify. Let's see. What did you guys do to it first? You noticed a couple of squared trig functions. That always brings us, gives some options to us. So anybody have a recommendation on what they might have done first? Turn tangent into secant? How the heck would we ever turn tangent into secant? Oh yeah, those are identity for that. We know that 1 plus the tangent squared of x is equal to the secant squared of x. That's one of the Pythagorean identities, one of those secondary Pythagorean identities. So we could either turn the tangent squared into secant squared x minus 1, or kind of reconceptualize that top line as 1 plus tangent squared x all over secant squared x minus 1, and turn that into secant squared. Or if we had turned tangent squared into secant squared minus 1, the ones would have canceled, so it would have worked out the same way anyway. So 1 plus secant squared x over secant squared x minus 1. That's a fairly reasonable start. Wiggle your fingers and say the magic words. Abracapythagorean identity. Those magic words. What do you want to do next? Turn the secants into their own fraction thing. Pill the secants into separate. That probably meant split. Pill. Either way, I know what you mean. Divide that into both of those. Pull. Oh, pull. Okay. Pull makes more sense than turning that into split. So that turns that into 1 over secant squared x plus secant squared x over secant squared x. I'd probably say divide the secant squared into the upper terms, something like that. However you want to say it. 1 over secant squared becomes cosine squared plus 1 minus 1. So cosine squared x. That's a nice answer. So yep, I think the Pythagorean identity is the way to start on that one. Certainly there are other options. There are the people who always like to turn everything into sine and cosine. I've told you guys I'm not a big fan of that, but it certainly often works. If you did that, all you'd really have to do is multiply by cosine squared x over cosine squared x. That would turn that denominator into a 1. We'd get 2 cosine squared x plus sine squared x minus 1. Actually, it's kind of nice this way. You do have to recognize that that leaves us with cosine squared x plus cosine squared x plus sine squared x minus 1. So you can turn this into a 1. That's probably the hard step that way, is splitting up that 2 cosine squared x. So that's a little conceptually icky, but works just fine too. There's certainly other things we could have done. We could have turned this. Just always options. Yeah, often it's a little bit ickier, but sometimes it works out nicer. Sometimes it works out a lot worse. This one wasn't a lot worse. It's just thinking to turn that 2 cosine squared into a cosine plus cosine isn't the easiest thing to do. There's probably something you could have done turning the denominator into 1 plus tangent squared, but I don't like multi-term denominators, so I think that would have been a little bit worse probably. Yeah, I would have done that. That just but options. Why don't you guys take a minute? If you have any questions on that simplify, let me know. But take a couple of minutes. I'll give you 2 or 3 to solve that 5 sine 2x minus 5 pi over 3 plus 2 equals 0. So we have one of these solvings that we can practice that actually has a solution. So that's, of course, the big step, getting the principal inverse and then creating the secondary angle, or secondary angle if you want, or secondary inverse if you want. Principal inverse is a technical term. Secondary inverse is not a technical term, but I think it's a reasonable thing to call it. So we do get that one principal inverse from the inverse function on our calculators. That's what gives us this point, or negative 0.4115 in radians. We could have gotten the other one by, adding pi to that negative, but we would have had to have been going this way with, I think it's like 2.7 or something, so negative that. So that would have worked too, as long as your signs were right. We did know we had to be in quadrant 3 and quadrant 4, because those are the quadrants where sign is negative. So that negative 2/5 tells us we're going to be in those bottom quadrants. And then, of course, we have to remember to add our coterminals. So we have to remember to add the 2 pi k. Even though we only want answers within the interval from 0 to 2 pi, that compression factor of 2 means we're going to get extra solutions. So we need that those extra periods to generate those extra solutions. So we always do want to get the general solution first, which we're not done with yet. So this is just that first big step of breaking the problem into 2 pieces. A lot happens in that step of take the inverse function. So questions on that step, it's probably the biggest step there. Everybody okay with that step? Get some yeses or some thumbs or some woo-ha. Smug looking nods, they work too. Thumbs up, all good. Okay. The rest of it's nice because it's just algebra. So we're going to add the 5 pi over 3, add the 5 pi over 3. It is a little irritating that we have to use decimal approximations for all this the rest of the way. I think Felix was talking the other day about, gotten sick of decimals now. So true. So plus 5 pi divided by 3, 8.789. So 8.789 plus 2 pi k. And the other one, that one, plus 5 pi over 3. So that's a 2x equals 4.824 plus 2 pi k. If I do anything weird with these down here, let me know. Divide by 2, divide by 2. So our general solution be what, 2.412 plus pi k. And this one's harder. 39, probably 39.4 plus pi k. It was a 0, wasn't it? 9, 0, 9, 7, 2, 5, 6. 4394, 4394.5 though, so it does round up. Barely. But okay. If we're keeping more decimals. So those would be our answers in our general solution. But we are asked to give the solutions between 0 and 2 pi. So we certainly already have some of them. The 2.412 is certainly between 0 and 2 pi, as frankly is the 4.395. So for both cases, our k equals 0 generates a solution in our interval, and over here, k equals 0 generates a solution in our interval. So that's nice. K equals 1 here would be 4 plus pi, so that would be 7-ish. So that's too big. K equals 1 here would be our 2.412 plus pi. So that's only going to be 5 and change. So that's going to be a reasonable solution. So whatever that is, 2.412 plus pi, 5.55. Okay. So that's going to be 5.554 when we round up. So that's going to be another solution, because that's less than 6 1/4, or 2 pi. If we went to k equals 2, that would be 5.5 plus pi, which would be somewhere in the 8s. So 8-ish, which is too big. So no. So those are 3 answers, and we're good? Yes or no? Oh, what about -1? Well, -1 couldn't possibly do anything, because here, if we took that 2.412 and subtracted, let k be -1, subtracted pi, that's going to be negative. So that's too small. Ah, yes, but you all yell, because this is bigger than our period, our modified period. The 4.395 minus pi is going to leave us with something. So absolutely correct. I knew I could count on you guys. So that minus pi is going to leave us a 1.253. 1.253. So 1.253. If we subtracted more pi's, it would be too small, so we know we're done. And we expected 4 answers, because we expect 2 answers per rotation. That 2 is going to make answers come up twice as much. So 2 times 2, we expect 4 answers. We got 4 answers. Does the order matter? No. Set notation, sets by their definition don't include order. So order doesn't matter in set notation. It can be nice to put them in order. It can be polite, but sets aren't ordered. But it can be polite. So questions about the solving. It does take some practice. The big thing is properly breaking it up into those multiple pieces. I want to ask you guys, do you guys want to work on another solving example, or do you guys want to play with the angle, sum, and difference formulas that we've been talking about the last couple of days? Would doing another solving be good for you guys, or do you want to try something else? Do let me know. I want to hear from preferably everybody, if not, because I want to know how you guys are doing. We got a vote for solving and a vote for something else. The rest of you are thinking very hard about what it is you need or want. A solving from Nicholas, solving from Garrett. Well, let's try doing this. Let's respect both of those things. Let's try a solving of a type we haven't done. So I don't think we've done a tangent solving together. So let's do that. Let's go with 4x minus, let's just go with 3. And we want that to equal, could equal anything's tangent. 7, why not? And let's solve 4x in, actually, no, let's just do it this way. Solve for x in that same interval. I don't want to get too weird with these. But I don't think we've done a tangent together, and tangent has a little something extra that happens. So that'll hopefully satisfy Nick's something else in there. So I'll give you a couple minutes, then we'll do that real quick. So certainly the first thing you're going to do is divide off that 8, right? Then you will invoke that inverse function. Invoking that inverse function breaks us into pieces. So our 4x minus 3 equals our tan inverse of 7/8 is 0.788. And that's in quadrant 1. So 0.788. Now here's the fun part. What's the other quadrant where tangent is positive? Isn't it kind of cool that 7/8 gave us 0.78? Anyway, what other quadrant is tangent positive in? Shay says quadrant 3. So it's going to be, the other answer is going to be down here, such that that is the same 0.788. So those two rays are pointing exactly opposite from each other in exactly a straight line. So that angle between them is just pi. So we can actually get the other answer by adding pi to that. That gives us that secondary answer. This always works for tangent, by the way, because tangent is positive or negative in opposing quadrants. This is always going to happen. But even better, if we wanted to get back to a coterminal to our first answer, we can just add pi again to that second answer. And then adding another pi gets us coterminal to our secondary answer. Adding another pi gets us coterminal to our first answer. So instead of having to break this into two sets, we just add pi times k, and that gives us all the coterminals to both our primary and secondary answers. Now, it's still two answers per rotation and all the coterminals, but because of tangent's structure, we get to write it in its condensed form as one set instead of two sets. And you might remember when we graphed tangent. Remember, tangent had a period of only pi, right? Sine and cosine had a period of 2 pi. They repeated themselves every 2 pi. Tangent had a period of only 1 pi. So its answers naturally come up faster. So we could write it as the two sets if we wanted to, but take advantage of the fact that tangent has that nice short period. Then if we wanted to finish this, add 3. So 4x equals 3.788 plus pi k. Divide the 4, and x equals 3.788 over 4 plus pi over 4 times k. And might as well figure out what that is, that 3. Is it 788 or 7188? It's 7188, isn't it? You guys aren't watching out for me. Dominic, you gotta tell me these things. You tried? You said they're going 1. That's fair. Okay, divide that by 4. So x equals 0.9297 plus pi over 4. Okay, so that's our general solution. If we want our general solution, that would be it, and we'd be done. It is, again, just one piece instead of two pieces. It's the benefit of tangent. But if we wanted our solutions but from the or in the interval from 0 to 2 pi, we'd want to start playing with our k's. So k equals, we'll have some zeros, k equals 1, and we'll see when they get too big, and we won't forget that we want to at least consider negatives until they're too small. What is pi over 4 about, by the way? It's about 0.7-ish. Now that's a real gross approximation. It's closer to 0.8, but 0.7, 0.8-ish. It's a little more than 3/4, so it's a little more than 0.75, so 0.8-ish, just so I can have an approximation in my head. So the k equals 0 is going to give us the 0.9297. That's certainly in our range. Adding pi over 4, 0.9297 plus 1 pi over 4 is going to get us to about, what, 1.7? 1.7 still well within our range. 9297 plus 2 pi over 4, so it's going to be pi over 2. So pi over 2 plus this little angle, that's still going to be well within one rotation. 0.9297 plus 3 pi over 4s. 3 pi over 4. Well, even if we look, where's 3 pi over 4? 3 pi over 4 is right there. Adding 1 radian, that's still going to be well within our first rotation. You could calculate all these, but I like to remind you don't have to. So 3.14 plus 9 or 0.9, still going to be less than 2 pi, certainly. K equals 5.9297 plus 5 pi over 4. 5 pi over 4, again, is down here. 1 radian isn't going to get us to 2 pi, so keep going. That's 6.9297 plus 3 pi over 2, or 6 pi over 4, so 3 pi over 2. Now 3 pi over 2 starts getting interesting. 3 pi over 2 plus 1, well, there's another pi over 2 radians here. Pi over 2 radians is 1.57. So there's enough room for a 0.9, because if there's 1.57 left, there's enough room for a 0.9. So that point's good as well. But at k equals 7, the 0.9297 plus 7 pi over 4, that's going to be too big. Now, I'm only doing it this way to kind of show you guys that, we can figure out which ones of these are too big and too small without necessarily having to know their approximations. Oh, yes, I would certainly, or you could set up an equation in your table and have it crank them all out. So lots of different ways to handle this, but I like to remind you guys that we know what radian measures are. We know about how big they are. So how many answers is that? That's 1, 2, 3, 4, 5, 6, 7 answers. Well, how many answers did we expect? Well, 2 per rotation times 4. We should be expecting 8 answers. Well, luckily we have some negatives. 0.9297 minus pi over 4. Again, pi over 4 is a little bit less than 0.8, so that's going to leave a little bit of positive left behind there. Subtracting pi over 2. Subtracting pi over 2, again, pi over 2 is 1.57-ish, so that's going to be negative. So that's too small. So we'd certainly want to write that as a big solution set, but I'm out of time. So, and we could, find nice decimal approximations for those. And one of the reasons I wanted to do that way is if you wanted exact values for these, this 0.7188 is the only place that we're really approximating here, other than when we divide it by 4. So it's actually not uncommon when we're in situations where we need to stay exact or don't have values and we're just dealing with, abstract numbers here, for this to, instead of being 0.7118, this being the tan inverse of 7/8. And it's staying that way. So 4x would equal then the tan inverse of 7/8 plus 3 plus pi over k. So then x is the tan inverse of 7.8 plus 3 over 4 plus pi over 4. And we keep this exact. And the tan inverse has a maximum value, tan inverse of 7/8 anyway, has a maximum value of pi over 2 because it's in quadrant 1. So 1.57 plus 3 is, 3.57. So it would max at, actually 4. So it would max at 4 point something. 4 point something divided by 4 is 1 point something. And then you go through the same argument going, okay, which of the coterminals are going to work, without ever having an actual approximation for it. Particularly if that 7/8 had a variable in it, like it was a over 8 or something. So sometimes it is, kind of necessary for us to think about where these things are, what their limits are, and where our answers might live. Now, we're not going to have to do that in this class, but for those of you who are going on to particularly engineering, particularly electronics, do a lot of this in electronics. So Nick, was that something else enough for that work? You'd say so? Good. I didn't want you to be unsatisfied with that. For those of you who wanted the solving, was it nice to do a solving with tangent together? Yeah, okay, good. Okay. Do play with that. Hopefully your 7-3 homework is either done or almost done. We talked through all the different types of problems for the angle sum and difference formula. It's close. I don't know what's close, Martin. I don't know what that means. Oh, 7.3. Okay. So ideally that's all done, or close to being done. And so start working on the angle sum and difference problems. There's a more problems in that list than some of the others, but we did look at all the types. We'll talk a little bit more about those on Monday and do our double angle and half angle formulas. The double and half angle formulas are very similar to the angle sum and difference, and they're actually derived from the angle sum and difference formulas. So they should be familiar if you're nice and familiar with the sum and difference formulas. So go play with that stuff. If there's anything you need, let me know. And as always, have a wonderful day.